You only need to walk around the pits here at World Time Attack Challenge and you're going to find a number of the top cars are running MoTeC electronics. And at HPA, while we're completely brand agnostic, we've had a lot of experience with MoTeC ourselves. Back in the day, my old drag car set world records with an older MoTeC M800, and currently our SR86 endurance car runs a MoTeC M150. However, it's not too often we actually get to talk to someone who is in charge of developing the ECU and get a much deeper understanding of what goes into this. So we're here with Darren, who's a lead applications engineer at MoTeC, and one could argue is really the person responsible for the MoTeC M1 platform as it stands today. So Darren, for a start, let's actually talk about what your job title even means. What is an applications engineer? What do you do?
I make our ECU work in various applications. So whether it's a race car or a plug-in kit, for instance, there's a lot of CAN integration, a lot of new control systems that we need to write to integrate with the OE electronics that are there. So maybe there's a new thermostat which has a servo motor, which is becoming quite common, things like that. So it's my job to make those systems on the engine work.
So essentially reverse engineering the newest innovations from OE manufacturers and making sure that MoTeC electronics can control it as intended.
That's a much better way to put it, yes.
Let's go back one step as well. I'm interested, did you sort of grow up with a passion for cars and motorsport, or was your passion more around applications engineering and you've fallen into the role at MoTeC?
That's interesting. I grew up on a farm, so there was lots of motorbikes and tractors and things, and so there was lots of engines and engine building. And then when I turned 18, I started to get into cars, and then friends were going racing. So it goes from there. I had my own race car back in the day, a VL Calais. Yeah, it was when I decided I wanted to get a serious job, I went, where do I want to work? MoTeC. So applied for a job. That goes from there.
The reason I ask that is I'm interested, do you think that you could be as successful in your role and do what you've done if you didn't actually have a passion for motorsports and an understanding of motorsports?
No, yeah, you have to have a passion, I think. Yeah, it helps a lot. To see people succeed and to help people succeed, that's what really drives me. So to get that feedback that, hey, I won this race and and it was your help that did it, that keeps me going for sure.
That was my assumption, but I just wanted to clear that up. The other element is, what is your sort of educational background? What do you actually need to do in school or university or all of the above in order to become an applications engineer?
I didn't go to university, so it's kind of a learn on the job, but I'm the kind of person that if I want to do something, I just learn how to do it and I go and do it. And so it's been a lot of trolling websites and various things, talking to a lot of people, and that's where I've been had electronics as a hobby since I was very young, and then that turned into programming as just a hobby. So in those, when I was sort of 15 to 25, that kind of thing, and I was making my own electronics for my own race cars and doing various things, not ECUs obviously, but a little bit too far, but various little devices I'd build for myself, and that's where it came from. So.
I'm also just interested to get a little bit of insight into the development path of the MoTeC brand. I mean, I probably cut my teeth back with the old M4, which was DOS based, and at the time I felt was cutting edge. Now I sort of shake in terror if I have to tune one. Then the 100 series, which is what I ran on my old Evo drag car, and then obviously we've moved to the M1. So what drives the development requirements in terms of that sort of movement from M4 100 series and then M1? Is it a hardware requirement or the advances in OE electronics and engine technology that demand more sophisticated control strategies?
Absolutely, yeah. And obviously the one of the biggest drivers there is emissions. It's not something that we have to dabble in, but engine technology is really pushed hard by the emissions regulations, and so things like I mentioned, a servo-driven thermostat is driven from emissions, but then you get a better heater out of your car and you get better temperature control and things like that. So yes, we have to evolve with the times, and technology keeps moving forward. So we're able to build newer, better products with the available processors that keep coming out better and better all the time. So we keep moving forward.
The next question that sort of follows on from this is, again, having used all of those platforms, one of the big changes, and we've seen this across sort of a broad range of aftermarket standalones now, is that move from an injection time-based fuel model to volumetric efficiency or VE-based fuel model. So for a start, could you give us a brief sort of high-level view of what injection time-based fuel models are versus VE, and then also why we've changed?
Yeah, sure. So the time-based is under an operating condition, being a certain engine speed and a certain engine load. We say we want the injector to open for a certain amount of time. And that takes away any changes in fuel pressure, which would alter that time, any changes in air temperature and lots of other conditions that affect the injection opening time. Those kind of compensations are applied in terms of tables, and so then you have to tune those tables and you have to understand what you're tuning and what those numbers mean. Where with the efficiency-based model, we're taking the physical properties of air and pressure and things like that, and temperature. We combine them all together to figure out how much air is flowing through. So the efficiency-based model is not about calculating the fuel, it's about calculating the air. And then we apply lambda on top of that. What target lambda do we want? And we have a characterization of the injector, which includes pressure, the fuel pressure. So once we know how much air there is in the engine and what lambda we want to run, then we know how much quantity of fuel to inject. And so if we want to then go and change injectors, we can change the injectors, change the injector characterization, but our efficiency model doesn't change.
So this was one of the big problems with the injection time-based, which still works absolutely perfectly when it's just a bit more work for the tuner. But a common modification that I would be retuning for as a tuning workshop owner back in the day was customer would bring in a car, we'd tune it, basically max out the injectors, so we sort of cap that at whatever we're comfortable with, and then in 2 months' time he comes back with a new set of injectors that are bigger. You put those in, but then it's not quite, but it's almost a case of really completely retuning that fuel table or injection time-based table, whereas, as you mentioned there, with the VE-based or efficiency-based model, as long as the characterization data for the injector is correct and accurate, and you swap to another set of injectors with that same data, it really is just plug and play, and essentially the engine should operate exactly the same. Now, should is the operative term here. It's not always perfect.
Always a
but
fine tune needed.
Generally, maybe you'll be within 1 or 2%, maybe 2 or 3% at most. So definitely takes a lot of work off the table for the tuner. You also mentioned the compensation table. So conventionally, we would have on an injection time-based model, we'd have a compensation table for intake air temperature, and then it's up to the tuner to actually fill that out at this load and intake air temperature. How much should I trim in or trim out? And there's some rules of thumb around. I sort of work on about 2.5% fuel per 10 degrees C change, but that's not always going to be absolutely perfect. Now with VE-based, this is all incorporated into the base fuel model, so we don't have to think about it.
It's not so much you don't have to think about it. There's always still, you want to change things when air temperature changes, but the hard work is done. Yeah. That's definitely the hard work. So,
actually, while we're on that, and it's just something I wanted to dive into a little bit deeper. So, when we're looking at intake air temperature compensation, and whether that's just a 2-dimensional, a 3-dimensional table in a conventional injection time-based ECU, or you're trimming on a VE-based fuel model, really that's kind of a workaround because we're measuring the intake air temperature, but what we actually want to know is the charge temperature as the air's entering the cylinder, don't we? And that can actually be affected by air speed. So what I mean by that is at low air speeds, idle, light throttle, there's a lot more transit time for the air. Once it goes past the intake air temp sensor, then it goes into the inlet manifold, can pick up heat from that, then the intake port. So the actual charge temperature can be different to what the inlet temperature sensor has told it. Can you talk us about the complexity that adds and any workarounds? And I know there's not an easy workaround.
It depends where your air temperature sensor is placed and the speed that it reads at and a few things like that. But generally, we try and take the sensor as gospel, if you like, that it's reading the right value, and we compensate on that. And so the air temperature effect on the efficiency is always applied as the temperature. We do have a model to try and model what the temperature of the housing of the manifold is, and so that how that affects the air temperature as charge temperature. But the biggest effect is the cooling effect of the fuel. So when you spray the fuel in, that evaporates and takes a lot of the temperature out of the air. So we have a different characterization for that as well. And it's kind of, how would I put that? It's not so strict in the way it's done. We have quite a loose kind of method of doing that, and you just tune it. And it generally is only one number, and it can be a table with air temperature as well, but you can tune it with one number. And it's a case of, once I change my target lambda from, say, 0.95 to 0.85, how much cooler is the air? So then you end up with a little bit more airflow going in, and that will change the mixture. So then we use this
charge cooling coefficient.
Yeah, exactly. So if you change the lambda target for exactly the same operating point, that your lambda should stay on target.
Which is, I know from experience, is reasonably easy to dial in. Which sort of gets into the deeper question, which I wanted to get to, is that engines are complicated. There's a lot of elements that will be different from one engine to another, and trying to get a simple or relatively simple model to work across the entire range, be universal across almost any engine, is difficult. So then you can add more and more complex inputs required from the tuner in order to sharpen up that model and get it more and more accurate. But of course, then you're asking more work from the tuner.
Correct.
So how, as an applications engineer, do you sort of weigh up the accuracy of engine control, basically getting the right result, versus giving the tuner something that you don't need a PhD in order to actually tune?
Yes, it's a fine line to tread, and our higher end customers always want better control, and our lower end customers always think it's too complicated already. So I tread that line based on experience from dealing with our customers and knowing what that level of competence is out there. So if I definitely have some higher end customers which say, why don't you do it this way? And I have to say, I know it's wrong, or I know it's not 100% right, I should say. But we have it this way because it's generally too hard for our customers to tune. So it is a fine line to tread.
And I think that's something that our listeners, those who are tuning for themselves, probably need to keep in mind as well, irrespective of the platform they're tuning on. Everything is, of course, in life is compromise, and you're trying to tread that, as you say, that fine line to make a product that works well for the largest number of users. Now, I also wanted to talk about when the M1 was in its infancy. Really, one of the first and biggest projects that you've worked on was the integration with the Nissan R35 GT-R. So this is a pretty complex car. I mean, it's mainstream today, but particularly at the time, this was a leap ahead for Nissan. It's a very complex vehicle. So for a start, what drove the decision to support that platform with a plug-in variant of the M1?
It was just the most logical choice at the time, for sure. We'd done the plug-in kit on the M800 for the Evo 10, and it's kind of just, it was the next big car that had come along. And I'm a Skyline fan from way back. I've had a couple of R32s myself, so it was one of my passions. And we had the opportunity, or had access to a car by a very nice guy who races locally in Melbourne, and he didn't use his car very much, and basically he loaned it to us for a few months at a time here and there, and we were able to it was basically the access to the car really that allowed us to make such a complete kit and make it all function correctly. But yeah, it was I'm getting a bit lost here now.
That's all right. In terms of that platform, you've got not only the sophistication of running the engine, and that part in and of itself is really not too complex, but then there's the integration with the other OE electronics and CAN bus, and then most importantly, there's also the integration with the transmission control unit with what is a dual clutch transmission. So that needs some very, very complete and careful communication backwards and forwards between ECU and TCU in order to enable the shifts to complete. So I guess first up, what was the most complex part of the process for you?
Okay, getting the upshifts to function as cleanly as OE, that was always the goal, to make it drive as factory as possible, and so it was just a lot of data gathered. We looked at what the OE ECU was doing and the sensors that it had, where it has one manifold pressure sensor where it's a dual plenum engine, but 2 boost sensors, and that straight away told us that, hey, Nissan are using the boost pressure and a model of airflow through the throttle to actually manage the torque in the engine, where most of the shift torque is controlled by ignition timing. So then there's also many times for the OE traction control that's based from the ABS, where it's commanding a torque via the throttles. So there's the 2 factors there. There's torque controlled by ignition timing, torque controlled by airflow, and then marrying those 2 systems together. So I guess the hardest part about the integration part with the transmission is about getting those 2 systems to work together and control that torque accurately.
So let's come back to that in a second. So my sort of rudimentary understanding of this is essentially the driver requests an upshift. That signal goes to the transmission control unit. The TCU then requests a torque reduction to the ECU, so it requests a specific torque value. It waits until the monitored torque reaches that, then it will progress the shift, and then once the shift is deemed to be complete, it will say to the ECU, right, you can reinstate full torque. Is that about right on a simplistic view?
It's roughly right, yes. Based on operating conditions, because if you're full throttle or half throttle, it's quite different. It will request lower torque, and for a moment, and as the engine speed falls, it will ramp. The TCM will request that the engine ramps the torque back in progressively.
So we've kind of got an understanding of what happens there, and we're only talking about the upshift for the moment. Let's just keep it relatively simple. Then you mentioned there's 2 strategies of torque request essentially from the engine. You mentioned throttle control, and then you mentioned ignition timing. So essentially with the ignition timing, we retard the timing, we make less torque. Throttle control, we close the throttle, obviously the engine makes less torque. How do you decide which of those 2 strategies to use?
The transmission tells us. So
okay, so it's actually telling you what to do.
2 different torque numbers. It's either requests this torque number and says, I want ignition timing, or it requests this torque number, I want throttle. And sometimes it will do both at the same time.
So does that come down to whether the shift request has happened at part throttle where the engine isn't producing much torque, or a wide open throttle on a full pull on the open road or a drag strip?
Yeah, it's almost always for shifting using the retard based. It's just a much faster response, obviously. And it will use the throttle based during downshift. So you get that smooth transition once it's blipped, that it pulls the throttle torque down to then go back into overrun usually.
Okay, so this leads us to the next complexity. We've talked about the M1 traditionally being a volumetric efficiency-based ECU. Now we're bringing in a torque model as well. So I'm interested how, and not having actually tuned an R35 myself, how does this work from the tuner's perspective? What additional complexities are there? Because again, this sort of comes back to what we were talking about. You want good, accurate control, and obviously in this instance, the torque management is very, very critical, but you don't want to make it too hard for the tuner.
Yep, so we don't have a method of measuring actual torque out of the engine. There's no torque sensor. So we relate torque back to engine load, and engine load being the mass of air per firing of the cylinder. And there is quite a close relationship between those 2 points, and we just take it as literally a straight line, linear interpolation between this engine load is this much torque generated. From that point, the things that become more important to tune correctly is the efficiency model itself, because the efficiency model is telling us how much air is going into the engine. So Actually, I'll stop you there for a moment, because this is one of the complexities. I know I've seen this myself because I've
fix some errors. A lot of people that came from the traditional injection time-based fuel model, moving into efficiency-based and not understanding the logic flow of how that works. And what I mean by this, you already mentioned, you've got a lambda target table, and that's one of the first places we need to start. Basically set our air-fuel ratio or lambda targets to realistic. What do we actually want for a given RPM and load? Then, and it's also, we need to fill in information about the fuel that we're using, the injector characterization, as you mentioned, we need the engine capacity, and this all needs to be accurate. So it's very easy if you overlook those elements because you don't know how important they are. Yes, you can still tune the engine, but what you're actually doing is fudging the numbers in the VE table and they're no longer accurate. Then when you bring in this torque model, you now basically built yourself into a corner, correct?
Correct, and that's what I was trying to get to, is the accuracy of your injector calibration, of your manifold pressure sensor calibration, and all of those other factors, the displacement, as you mentioned, they all have to be correct so that the ECU knows how much airflow is going into the engine. And then the torque control from that point is actually a model of the throttle's airflow as well as the engine's airflow. And that way we can, for a given throttle position, if we know the pressure upstream and the pressure downstream, we can calculate the flow through the throttle. So the main additional tuning component for torque control is literally just a two-dimensional table of the throttle opening versus the throttle blade position, throttle area, of how much flow can go through the throttle for a given blade position.
So at that point, then the ECU can accurately calculate the mass flow that is passing through the throttle into the engine. And if we know that, really everything else falls into place.
Yeah, that's it. Yeah. So flow through the throttle, if you're at steady state, it has to equal the flow through the engine. And to get to those two flows to match, the model changes the modeled inlet manifold pressure. So it's if there's not enough flow going into the engine, then the model will just increase the manifold pressure. And so those two numbers then will always balance out. And if the model's tuned correctly, that will also equal the sensor's value. So,
yeah. No, I mean, I think that all makes sense. Probably pretty heavy going, but maybe if our viewers aren't quite picking this up, another run through this video might be well worthwhile. So once we've got this model working, I mean, we've already talked about the fact that it's necessary for the TCU, but it also gives the tuner some other functionality, particularly with obviously the R35 drag and roll race market is very popular worldwide, and these engines now producing 2,500, 3,000 plus horsepower, and torque management is key to getting that power to the ratio. So what tools have you then given tuners to put in their tool belt in order to manipulate the torque versus gear versus road speed or whatever it may be?
Everything and anything I can think of. So yeah, as you mentioned, there's a gear-based torque limit, there's a vehicle speed-based torque limit, there's an overall torque limit, there's a wheel torque limit, so we'll automatically calculate the engine torque from your requested wheel torque. We have a whole traction model, which models from tyre friction coefficient, so how much grip your tyre has, to then work all the way back to how much engine torque we can supply where that tyre will just start to break traction. So there's lots and lots of tools we have in there to help make those cars go down the track as fast as possible. So
essentially, from the tuner's perspective, you've given them the ability to almost always match the amount of torque being delivered to the tyre to the amount of grip that tyre has, so you're never overwhelming the tyre. And the benefit of that then is if you do end up with wheel spin, it should be a relatively small amount of wheel spin, which makes the traction control strategy less heavy-handed.
Yeah, that's exactly the purpose of the traction model, is to just give the wheel a little bit more torque than it can handle, and then let the closed loop part take up the rest, because if we're not turning the tyre, there might be a little bit of tyre left, and we don't know. So to overshoot just a little bit and then let the closed loop side measure slip and reduce torque either via cut or ignition timing, as well as closing the throttle. We have all of those methods available.
This also begs the question, on a four-wheel drive platform like the R35, how do you accurately know when wheel spin is occurring? Because my experience with four-wheel drives, albeit much simpler four-wheel drive platforms, is when you wheel spin, all four are spinning. So give us some insight into this. Are we talking high-speed GPS, or what's the story?
So we can use high-speed GPS, and we have plenty of customers using that method. The built-in method is generally you don't really get all four wheels spinning all the time. There's always one that's typically you're loaded a little bit left, a little bit right, and one that will be traveling at the true ground speed. To go past, if we do have all 4 spinning, we have a maximum acceleration rate that you can set. And that means that if all 4 all of a sudden jump up in speed by quite a bit, we'll have our actual speed only creep up at a certain rate. And so that will then, the traction controller will work to that factor. And so that's just quite a simple method. Once you go, we can use a longitudinal G sensor as well to correct that factor. But once you go off the drag strip and go into some track racing or driving on the road and where you have hills, the G sensor method starts to have a lot of inaccuracies. So
limitations depending on the application.
Yeah, and it's a limitation in the OE world as well. It's very difficult for even the OE with many hundreds of engineering hours to accurately calculate a true ground speed from wheel speeds.
I mean, I guess the OEs have the benefit that they know that the platform isn't going to be messed with and isn't changed. You're dealing with something that could be making 600 horsepower or 3,000, and you're trying to use the same strategy to sort of go across that entire range. Now, that strategy, the torque model, as I understand it, also sort of been inherited by the Audi R8 and Huracan platform, which is also incredibly popular for drag racing and roll racing. But it's recently also made its way into the production firmware for an off-the-shelf M150 that can be used on any car with GPRP Pro. So is that just essentially exactly the same, but for any car, not just a GTR?
Yeah, correct. It's an evolution. So we started with the GTR. The GTR used a torque model, so we developed a torque model to run that car correctly as the OE runs it. It was the logical choice to use for the Huracan since it already had DSG integration with it. And then with the Huracan came a few more challenges as well. So when we moved to that platform, we moved to a torque-based throttle pedal. So in the older GTR firmware, up until about 2018, we used our traditional pedal to throttle translation. So it was just a table where for a given pedal position, we got a given throttle blade position. The torque model worked on top of that, but it was that direct relationship we still had up until that point. With the very responsive V10 engine in the Huracan, I found that to be quite difficult to drive and to make a nice feeling throttle pedal. So I tried to instead command a torque from the throttle. So we now moved to that method. It worked fantastically in that car, and I've had very, very good positive feedback about that, using that method from here.
Again, that's really the method that OEs have been using for a fair amount of time in terms of it's a driver's torque request from the pedal, which is really what we're asking for, isn't it? You know, we put our foot to full throttle, we want all of the torque the engine can produce.
Yeah, so we made that move for the Huracan platform, and it's just been a progressive development path. Actually, right since the start of the GTR, it's just been a progressive development path, continuing to build on top of that torque model. I had a job back in 2018 running some IMSA cars in the US. So these are Le Mans style cars. They're called the DPI, Daytona prototypes. So we fitted our ECUs to one of those cars, or two of those cars actually, and for that class, they use a balance of performance using manifold pressure. And because we can control manifold pressure with throttles, we could get a lot better response than trying to do it with boost control. So
there's a faster system than basically trying to see the boost pressures increased and then changing the wastegate position and waiting for the turbo to respond, and then it affects
the throttle a little bit and have the same results. So much faster reacting. The cars ended up going from midfield to winning races immediately. Then they got penalised with weight penalties, as happens. But from that point, I then built a torque package that then had paddle shift control in it. So we've had this sort of under our belt for quite a few years, and it was just with COVID and things like that, and we had a little bit of extra time, I guess, or we're all working from home, and so it made it into a few of our employees' cars at MoTeC for a little bit of testing. So this grew the general purpose GPRP Pro basically just as a natural progression of that firmware.
On that note, let's just talk a little bit about the sort of commissioning and validation process of a new product like that GPR Pro. You mentioned that it went into some of your employees' cars. What's that testing look like? How long is it before you sort of start pushing it out into the greater public? And then when you start doing that, do you have selected dealers that are preferred for doing some of this testing before it actually gets a general public release?
Yeah, for sure. There's various dealers that we have that we prefer for doing various testing. Ones we know that are very competent, that will give us really good feedback, really good data logging feedback as well. And so those people are instrumental in us developing these kinds of packages. So we can't have all of those high-end race cars in our workshop at any time.
They get pretty expensive.
Yeah, that's right. So we definitely rely on our dealers a lot for that sort of information.
I guess the next obvious question is, where do you see the future going? I mean, what are some of the developments you're monitoring in the OE world or the professional motorsport world that you see filtering down? Anything else that you can share with us that you're excited about sort of working on and seeing some improvement from?
Good question.
Without sort of giving too much away, obviously, some secrets must be kept.
Yeah, we certainly have. We have constant hardware development going on. There's always we have our whole engineering team working on various products at various times, and we are always pushing forward, obviously. So we do have a new ECU platform that is in the works, that's moving forward, I would say, without giving too much away. The constant development we're seeing in engine technology as well just keeps driving us forward too. So we need faster processors to do more work. We need more outputs in our ECUs to control more devices as engines just get more and more actuators fitted for various things. So, we used to have one boost control solenoid. Now we're seeing 2 wastegate servos, and so that takes a lot more.
So the hardware essentially has to evolve to suit what is being developed in the OE world.
Yep, and then that filters down into motorsport as well. So those engines then get used in a race car, and people want to make a lot more power out of them. So then and have all that flexibility in the tuning as well. So yeah,
I'm just wondering, in terms of the limitations as you currently see them on the M1 platform, and obviously there's a variety of different models within that family, the fact you mentioned you're working on a new ECU, what has become the sort of bottleneck, I guess? Is it the I/O? You mentioned obviously newer engines, more actuators, more things you need to control, so that affects your input and output requirement, or is it the processor itself needing to do, as you said, more calculations more quickly, or is it all of the above?
Yeah, it's all of the above for sure. So once you go to a DI engine with dual drive by wire, we start to run out of outputs quite quickly in our current series ECUs. Yep. So we actually use one of our M130 ECUs as an expander for, say, an M142 DI ECU, and so then we can then easily run port injectors on a DI V8, for instance, as well as all of the other actuators on the engine as well.
So you've got options, but a new platform is going to give you more flexibility.
Yeah, and it's a cost factor as well. So it's having 2 ECUs versus 1. So yes, the number of outputs or I/O in general is certainly a factor, and processor speed is certainly a factor with the communications getting hot. The demand on communications getting higher and higher all the time. So then there's also new communication standards like CAN-FD coming through. We're starting to see those too. So we have to evolve with the times.
Never a dull moment, essentially. Look, it's been great to get some insight into what goes on in the applications engineering department at MoTeC, and how you're taking these new technologies from OEs on board and integrating them into something that we in the consumer market can actually use. Thank you very much for your time, Darren.
No problem. Thank you very much.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.